All right, welcome to everyone attending virtually and those here in person as well. We have a pretty good turnout here, around 30 or 40 of our team members and fellow Purdue students. Welcome to our annual design review for our competition team. Our team this year is sitting at about over 100 members. And over the last year, we've had a pretty good fundraising run, over $55,000 to help grow and mature some of the technologies that we'll outline today. And here, just a quick outline of some of the great things that our members have done and some of the places that they've worked over the past couple of years. So today we'll be outlining the project that's being developed by the main branch, largest branch of our student team. That's our competition team. And the way that we've structured our organization this year is a bit different. And we're doing this to kind of eliminate some of the problems that we've seen in engineering integration. So we've moved to a product-based system. And so we're going to have each of our product lines, which are outlined here. There are 7 of them, go through their technical designs. And we're looking for feedback from all of you on these designs. And just to kind of give a brief timeline and schedule of what we'll be going through today, in the first 30 or 40 minutes here, we'll be looking at more of the mechanical perspective, as well as some of the aerodynamics and more aerospace related topics. We'll then move into the software presentation from 6:15 to 6:45, and then finally conclude with the electrical side of things. And hopefully we'll have some more folks joining us for those parts of the presentations as well. So the way that I'd like this to be structured today is to be an open discussion. So if any of you have questions, pending thoughts, feedback at any part of the presentation, please either raise your hand in the Zoom software or feel free to just unmute yourself. And sorry, there are a couple people joining in the waiting room here. Feel free to just unmute yourselves and kind of interrupt so that we can have a steady conversation. For those who are just joining now, to reiterate quickly, we're going through the competition part of our team, and we're going to be running through each of the product lines. And that schedule is outlined here. We're starting with the mechanical portion of the team, then moving to the software portion, and then we'll conclude with the electrical portion. So to give a bit of context to what we'll be outlining today and what the goal of this project is, I'll run you through this quick schematic which we've drawn up, which I think highlights the competition well. And this is a competition with about 80 to 85 teams out in Maryland. Usually it's located around Pax River, and it's a great place to learn, and this is really what we work towards every year. And we placed 7th in design last year. We're looking to place in the top 3 this year. So we have pretty high standards here, and I think that when we work through this presentation, that'll be quite clear. So the first kind of stage of the competition is to take off. And so this is a UAV, and all of the tasks need to be completed autonomously. So we take off autonomously before moving into a waypoint navigation section, which is estimated to take about 20 minutes long, and that's about over 12 miles of range. There's then an airdrop section in which we need to pass over a specified drop zone. First, the aircraft will be passing over that zone to detect targets. And so, there is going to be a variety of targets on the ground that look something like this star over here. And loaded onto our aircraft before we start the mission is a series of water bottles that have the description of these targets that are already laid out on the field. And so the goal is eventually to drop every one of those targets, of those water bottles that have those characteristics, on the appropriate target. And we'll talk more about how we do that in a few minutes here. But once we've passed over the zone and identified where those targets are, and then we've done a couple more passes to drop those payloads, then we will be landing, and that whole mission will take about 30 minutes, and the entire thing will be done remotely, or autonomously rather. So hopefully that gives some context. Does anybody have any questions really quickly, or is confused about anything in this schematic? Cool. So I'll hand it over to the Aeromechanical product lead, Corey, and he'll run you through some of the mechanical aspects of the aircraft.
Hello. So yeah, my name's Corey. I am representing the airframe team as a whole. I'm the airframe lead, but we have like 20 to 30 members on the team, and we've all put a lot of work into this so far. So to start off, before we get into the actual designs, yeah, my head's kind of way down. Before we get into the designs, we're going to talk about what the competition is and what we're doing in terms of airframe. So we're carrying all the software, the payloads, and there's some big changes from what we're used to last year. So this is a picture of our airfield that we're flying on in next year, so next summer. And that little purple spot there, that is our actual target zone. So Matt talked about the water bottles we're dropping. And those water bottles are all going to be dropped on targets located in that section right there. So the entire competition as a whole has actually added quite a few complexities for us. Last year, we were carrying around 1 kilogram of payload. Now we have to carry 2.5 kilograms of payload, which is 5.5 pounds there. So it's a heavy addition to our airframe. That's just the raw payload. So we have to actually make a chassis for the payload itself. So that's a lot of payload that we're not used to. In addition to that payload, we have a large range. So we had about 7 miles max last year. Now it's going to be a pretty guaranteed 12-mile range. So with the added payload mixed with the large range, there's a lot of complexity to make sure that this thing can meet both of those at once, because you can't really sacrifice either one or we're going to have heavy hits in our scoring. Another thing is we have to have stable passes over the target area. And because of the way the competition works, we want to have really slow, stable, steady things we can repeat over and over. So if we have a pass over, we see a target, we want to come back around and be able to repeat the same pass and have an accurate drop from the water bottle down to the ground. And then those things as a whole, we have a small airfield, but this is just, it contributes to a lot of parts of the airframe. So motor placement, ease of manufacturing, and maintenance are things to consider throughout. So an example of maintenance that's very important for us so far in our design process is if we say have a crash in our testing, we can't rebuild an entire carbon fiber airplane in a short amount of time. So we want to have parts that break specifically on a crash. We can replace those parts and then we're good to test again. So we had to consider all these things throughout. Now, Eric's going to Eric's going to talk about the aerodynamic sizing a little bit.
Hi guys, my name is Eric O'Keefe. I'm the mechanical systems lead for the team. So we're just going to kind of skim through the aerodynamic sizing. The actual process that we took started with a MATLAB script that took a wide variety of different inputs that actually gave us some basic parameters. And then from there, we were able to use that with some historical data to kind of build out this aircraft and the X-Flyer software. So right now with our estimated payload that we're going to be carrying, as well as all of our avionics, and then the battery that we were able to calculate through that MATLAB sizing script, we kind of came out to this 19 kilogram or 42 pound weight estimate, including the actual airframe mass itself. So going from this, we also wanted to fly anywhere between 30 to 35 miles per hour, around 15 meters per second. From our historical data, we found this is a pretty good speed to fly at. We're able to make our turns in the radius that we need to without pulling too many G's or banking too high. And it's also fast enough that we can fly into headwinds. At our test field, we have a pretty windy test field. So moving through here, we were able to create a solution that flies at that 33.5 mile per hour cruise speed with a 1.4 degree angle of attack built in. That comes from our stability analysis. We've only done a static stability analysis at the moment, but moving into dynamic longitudinal stability and then also lateral stability, those are things that need to be done still, but looking good. And then we also have a relatively low stall speed of about 24 miles per hour or 10.7 meters per second. This gives us a nice margin of error to play with in our cruise flight. And then coming in for landing, we should have a nice, slow, smooth landing. Sorry.
Question.
Oh, yes, go ahead. Yes.
How did you come up with that weight estimate?
So the weight estimate, we created a big weights and balances spreadsheet to begin with. So we included all of the payloads to start, and then we included all of the avionics because those were two constants that we knew we had to carry. From there, we were able to just use kind of historical data to ballpark how much we think the airframe is going to weigh. Then we were able to iterate a couple times and go through, and as our wings grew larger and larger, as we needed more area to fly at the same speed, we had to update that weight so that it was a very iterative approach. I think we did like 5 or 6 iterations of it to get to that. So I can share the spreadsheet with a little bit more data, but that also has center of gravity calculations built into it. So that we can place all of the different bulk masses, the lumped masses along the longitudinal axis of the aircraft. And then we can find our CG and make sure that it's in the right spot too.
Okay, follow-on question.
Mhm.
When you build your aircraft and it weighs 48 pounds,
Mhm.
why?
Yes, so the 42-pound mark is our estimate. Right now, it's also estimating about 33.5 miles per hour. We can bump this up to, I think it's in the ballpark of like 45 pounds to 48 pounds-ish. We fly a little bit faster, 15.5 to 16 meters per second. But all of the stability is the exact same because our CG is in the same spot. Ideally, we'd like to fly slow, so we want to try and keep it there. But anyways, moving on. These are just some of the plots from our static stability, our longitudinal static stability. So you can see we've got a static margin of about 16.6%, which is kind of in the ballpark of where we were last year. And with our different control surface sizing, we think this is going to be an appropriate place to start moving forward. And then our trim conditions at 1.4 degrees angle of attack. So I'll pass this back to Corey if there are no other questions regarding sizing. Okay, there you go.
So yeah, after those sizing decisions and all that, we're going to go into more the technical design. So we're going to use to meet that and how we're going to actually achieve those designs. But to start with propulsion, you can see we have a motor with a propeller on the back of the aircraft here. And then we made that decision for a few reasons. One of them was prop wash. We wanted to completely avoid any sort of dirty air coming back to the surfaces. Another thing was we wanted to have our cameras in the front. We wanted to have our avionics in the front. So we want to keep all of the magnetic presence from the motor and all the shaky vibrations, everything that was undesirable for those systems. We wanted to keep that in the back and keep the sensitive systems in the front. The actual setup of the motor is 450 kilovolts. We have a pusher, like I just said, 20 by 15 prop, pretty big prop, and we have this battery setup. We have a very loose estimate of about 7.2 kilograms from historical data and also from some calculations from the motor and battery specifications. Now moving on to the wings, we have this shape here. It's a polyhedral. We chose a NACA 6415. It gave us some desired characteristics of flight. The actual wing shape being a polyhedral, a large driving factor of that decision was the initial flat shape of the wing. So we wanted to make sure we had the ability to put a spar through the entire wing and then we could extend into a longer thing on the end. That is due to last year we had a very short spar and we noticed the wings weren't the best. And we also had a strict dihedral, which noticed helped. So we wanted to get the benefits of the dihedral with the strength of having a longer spar. So this is our solution here. And I'll talk more about the internal structure on the next slide. The span is 76 inches. That's per wing. So the total span is going to be a little less than 13 feet. We have an aspect ratio of 9.2. So it's going to have some pretty slow glidery characteristics that Eric already pointed out. And those are the angles there. So on the inside of the wing, we're using plywood to actually keep the shape and to keep the shape. And then we have an external carbon fiber skin. This is going to be pretty consistent throughout the entire aircraft. So on the fuselage, wings, stabilizers, it's all going to be plywood and carbon fiber. Again, I'll get more into that for the other ones as well. If you were to actually take the skin off the airplane, this is the rib structure you would see. So we have quite a few plywood ribs, and they're in reality going to be hollowed out. So we're going to save as much weight as possible. We decided to go with this because previously we went with this for our last year's aircraft. And sorry, how these messing with the computer here. Last year's aircraft, we used this system with the plywood and the carbon fiber, and it was incredibly strong and could take a large load. We tested it and it was about, I think, somewhere around 80 pounds, just putting weight on the wing itself. And we'll have some improvements for the layout and rib structure. The carbon fiber layout is twill and then unidirectional and then twill again. So it's going to have really good long stability, or it's not stability, strength across the wing as it goes out, so we can actually reduce the interior structure. The actual integration of the wing, this is the fuselage without the skin on the top. So if we took the skin off of the fuselage, this is the structures you would see. So we have some plywood structures and ribs within the fuselage that are going to have the spars going straight through them. So again, a large goal of the design here was to have a single shared spar throughout the wings. So we want to have all that force going into one. If you look closely, you'll see some little bushings on where the spars mount to those plywood ribs there. That is so if we have a crash, hopefully the skin stays fine, the ribs stay fine, And those replaceable 3D printed plastic parts, that's what's going to actually get hurt by the crash. So throughout this design, you will see things that are replaceable in the situation that something needs to break, right? And then we go on to the tail. So the tail is this shape right here. It's an unconventional shape. It's a V tail with a little downwards vertical stabilizer. We're calling that our Y tail. Now, the main driving decision for the V tail here is shown in those little streamlines you see there. So if we have the streamlines coming off the wing, that is undesirable air to hit the tail. It's going to be very turbulent, not the most ideal. So if we have a V tail going upwards, then it's actually going to be out of the dirty air. We want to be in clean air for controlling the aircraft itself. It's a pretty large tail. It's 30 inches each. So each one of those top ones you see is 30 inches long, and the chord is 10 inches. That's part of the aerodynamic sizing laid out by Eric. The internal structure, you've seen this before, it's the same thing as the wings. We have the plywood on the inside wrapped in carbon fiber. The only main differences is we have the twill and twill instead of the twill unidirectional and twill. That's because the stabilizer is really small. We don't really need to have that really long carbon fiber inside. And then we also have these spacers, which plays into the next part of our design. So these spacers are there because of the tail integration. If you take a look on the right side of the screen, you'll see the actual hub with the stabilizer attached to it. Now, those two little poles there, those are the spars, or not the spars, the spacers, sorry. And we're gonna have screws that are within the hub that pull the stabilizer onto it. So it's an attached separate piece that makes the tail itself. After making that piece, you can then push it onto the fuselage, and it's going to screw onto the fuselage. This was also heavily driven by the fact that we want certain things to break and certain things not to break. So all those carbon fiber skins, all of those plywood structures, those are the things we do not want to break. So our goal in the case of a crash or a hard landing is that the 3D printed part is what completely breaks on the aircraft, and everything valuable to us, again, the carbon fiber mostly, is going to come off of the aircraft. So saving those parts allows us on the airfield, on the test location, to take off the part that we saved, and we brought 3D printed parts to replace it. So we just replace them, put them on, and we're back flying again. All right. Now moving on to the fuselage structure, we have a very similar thing. Again, plywood and carbon fiber. Now, a big difference for this is the skin. Instead of just having carbon fiber, we're adding soric in the middle. Now, soric is kind of like a foamy type material. The most important part of the soric is that it spaces the distance between the carbon fiber, which allows it to be incredibly strong. What we noticed last year, we tried the soric out. We noticed that the fuselage was able to basically keep its shape, keep its strength without any of the interior structure at all. We could basically have a shell that didn't need any support from the ribs inside. So we're doing a mix of that. We're putting a little bit less carbon on the fuselage and a little bit more plywood within the fuselage. And we're hoping to get that perfect mix of strength, but also have a nice lightweight airframe. If you look at these ribs here, they'll probably be somewhat hollowed out to keep, again, the lightweight desire. We want to have a lot of lightweight on the aircraft because we're really tight with our payloads, as I discussed earlier. And then in the back, you can see we have that tail spar that was going off to the hub we talked about. That's glued straight in the fuselage. So this whole assembly you see here, that is the fuselage by itself. Now, the layout of the fuselage is also a thing that heavily drove where we're putting things and what shape the fuselage will be. So from the beginning, designing this fuselage, the goal was to have the minimum profile possible. Last year, a big issue we had was we kind of didn't know exactly what we would need in the fuselage because we were very new to putting these things inside of it. So we had just a very consistent square shape down the fuselage, and there was a lot of wasted space. And that large cross-sectional area results in a lot of drag. So we wanted to reduce the drag, and we made everything basically a function of what's inside of the fuselage. So you can see up front here, we have the avionics section. The avionics section is a nice stack of avionics PCBs that Kevin will talk about in a little bit. But those PCBs, the profile around it as small as it can be, which again increases the airflow. If you look at the wing hub there, that is just a very crude drawing of what it would actually be. So it's going to be a much smoother shape. So the fuselage is going to be very, very smooth throughout. It's going to be a smooth transition, so not much drag there, and very form-fitting. You can see the battery placement, those two blue cubes, those are where the batteries are intended to be. This also goes back to why we put the motor in the back. So if we have the motor in the very back, we can put less counterweights in the aircraft. We had an issue last year where a lot of stuff was forward of our desired center of gravity. So we had to use additional weight to weigh out and get the desired center of gravity. So by putting stuff really far in the back, we can then move the stuff that we need into the front and avoid any additional weight. And it really helps us out there. The middle there is the payload section. Evan's going to talk about that in a little bit. We have his entire structure for putting inside the payload section, dropping those water bottles out. On the bottom of the payload section is going to be some bomb bay doors, kind of like a World War II bomber that's going to drop out the water bottles. And again, in the back, we talked about the tail structure. Now, the tail structure, you'll notice, has an increased amount of ribs. So as we go to the back of the airplane, we want to really increase the strength to anticipate what's going to be back there, because we have a motor. Again, it's vibrating, it's very heavy. We have all of our tail structure, 3D printed parts. It's going to be a lot of weight, a lot of stuff's happening back there that we want to eliminate as we go into the main body of the fuselage. The landing gear was also a big issue last year. So last year we had landing gear and we really over focused on the issue of making it breakable in a landing, because in a landing, this is probably the part that hits the ground first. But we focused so much on making it weak in a landing that it got a little bit too weak for actually landing normally. So the front gear here is very beefed up. It's very strong. We have a large, strong bearing that sits flat across the fuselage. That large flat part there has the goal of, on a landing, distributing the force throughout the skin. Again, we have very strong skin on this aircraft, so we're trying to make that all distribute. And on the rear gear, we wanted to make it very easy. We had an issue last year of putting the gear on the aircraft was very, very difficult. And we had to go kind of inside the airplane and put screws on. This time, we're going to have it just sit flat against the bottom. So it's a commercial off-the-shelf landing gear that just screws right on the bottom of the fuselage. Now, as we move into manufacturing, there was very consistent methods here throughout the airplane. There was plywood and it was wrapped in carbon fiber. So for all the carbon fiber, we have gotten pretty good at our methods of making molds and laying it up. We're going to start using carbon infusion because, again, going back to issues that we were used to last year, we had kind of oversaturated parts. They were very, very heavy. So with resin infusion, we could just measure the amount of resin we want in the part and it'll just pull it right through and we get a perfect part. The molds are machined out of MDF and they are primed, and then we use them for our carbon fiber layups. On the bottom there, you can see our plywood frames. It's a pretty straightforward process. We have our computer part, it's laser cut, and then we glue it together. Some analysis we're going to do for the aircraft. We're going to do a full CFD test. We've done some basic X-Flyer tests that Eric showed you, but as we go forward, we want to consider more parts of the aircraft. So right now, all of our aerodynamic surfaces were determined using X-Flyer, and X-Flyer doesn't really care about a fuselage. But regardless, the fuselage is going to have added drag. So if we take our full assembly, put it into the CFD analysis, then we're going to have all of that airflow very, very well measured out. And also we're going to have more loads dynamic stability test on X-Flyer as we go forward. Some testing plans for the aircraft. We have a few plans. We're going to do some structural analysis testing. The most simple version of this is just taking the parts we make, putting weight on it, and seeing if it breaks. The desired weight that we need, if we're going to pull, say, 2 Gs, we have a 40-pound airplane, we need to make sure it can hold over 80 pounds of force. We also have potential wind tunnel testing. We might set that up later. It's just a more accurate version of our CFD. And then we're doing some prototyping. We have the ability to do very quick foam cut wings, very, very quick manufacturing of a mock-up of our aircraft. So it won't quite be the full thing that we've planned out with our carbon fiber, but it'll show us the actual capability of flight of the aircraft. We can simulate all that capability. All right. You were able to ask questions throughout, but this is an extra added question time if there are any questions, comments, critiques, anything like that. Charles.
Do you have any analysis or any plans to keep your avionics cool?
Yes, we do.
Carbon fiber.
Yeah, it's a good point. So the question, if you didn't hear it, was, is there any cooling for the avionics setup? So in the front of the avionics section, I believe it's actually backwards in this picture, but right here you can see that little black box there behind the green stuff, that's a fan. It'll actually be in the front in the real aircraft. So when we're on the ground, that fan's going to be actively cooling the avionics. And then when we're actually in the air, we're going to have slots, scoops cut into the fuselage to get airflow throughout.
Yeah, and just to add on, we can do a little bit, just to add on, we can do a little bit of thermal analysis for it. But the biggest thing that's going to be creating power is our power delivery board. We can measure the temperature on board. So it's probably just going to be experimental testing. And then we can bump up our fan speed to push more airflow or make a change on the fly if we need to. It's mostly going to be experimental though.
Does anybody have any more feedback on the mechanical side of the aircraft? Yeah, question.
Like, number one, you said everything's not that for what characteristics do that?
Thanks. Yeah, great question. So the question was, why did we select a NACA 6415 airfoil? This was the primary reason why we selected this one was it has a very high coefficient of lift. The standard airfoil that you'll find in a lot of databases is a 6412, which is a little thinner. That one would have helped us save a little bit of weight because it's less volume in general, but we chose to bump it up. So we can't actually find this one on a database. You have to plot it yourself. We chose the thicker airfoil because we'll get the stall to begin at the trailing edge better instead of the leading edge. So the separation is further back. It's a little bit of a smoother stall. And we actually get a slightly higher CL too, which is just coincidence, I guess. Mr. Staff or Saf, see you have your hand raised.
Yes, I was wondering why you chose to put the engine so far back. It looks like you have room to put it close to the bulkhead behind the payload.
Right here, a little
Yeah.
bit like closer in towards this hub that we've designed.
Yeah, I was just wondering why you would choose to put that weight that far back aft.
So a lot of it was actually attaching it to the airframe itself. So if you see the hub there, it extends to the rear of the stabilizer. And then there's the control surface itself that extends backwards. So a large part of the considerations there was using that extra space needed for the moving control surfaces and just sticking the motor attachment in there. And hopefully the real product will have the propeller mostly flush with the trailing edge of the control surface.
Okay, and have you looked at angle of attack on takeoff and landing to make sure that you have clearance?
Yes,
for the,
so
rudder.
Yeah, so that's something that is kind of a work in progress at the moment. Based on these like preliminary sizes, we're gonna have about a 10 to 12 degree angle of attack before we tail strike. That was another design consideration with going with the Y tail, is that vertical stabilizer acts to prevent a prop strike. That part itself skids. So we're between 10 to 12 degrees depending on the height of the landing gear. That's kind of the ballpark that we want to be in, we think. Last year when we were flying, we were coming in with an angle of attack on landing of about 5 to 7 degrees. So it would be pretty close, but hopefully with a little bit higher lift, a slower stall speed than last year, we can come in closer to like 3 to 5 degrees of angle of attack. That's kind of the plan right now.
Yeah, another thing about that was the landing gear team heavily focused on the length of the landing gear. So they tried to get a few inches of clearance from the actual ground plane to the bottom of the propeller. And in this in this picture you see here, in reality, the rudder is going to be angled upwards. There's going to be a bevel. So the part that takes the hit will be the stabilizer itself instead of the control surface, because it's a little more fragile. Yep.
Okay, that makes sense. Okay, thank you.
Cool. Yeah, thank you very much for your question.
Yeah.
Are there any others?
Hey, Matt, Rich Rayford, I have a question.
Yes, Rich. How's it
Yeah,
going?
good afternoon or good evening. Can you describe briefly the mechanization for the control surfaces? How are they driven? How are they motorized? Are they mechanical or locally digital or what?
They're digital. They're digital servos,
Okay,
9 or 20 gram servos. I forget exactly what they are, but there's a mechanical linkage on there. So it's just like on an RC plane. It's not too complicated.
okay, so it's just on the tail surfaces, not on the wings?
On the wings as
Yes,
well.
I did.
On the wings as well, okay, because I didn't see anything on the wings. That's why I was just asking.
Yeah, I don't know if the ailerons were catted in there.
Yeah, that wasn't calculated yet, but on the wings, where's the wings? If you look, yeah, right here, we're gonna have ailerons and also flaps. So basically the entire
Okay.
outer section of the polyhedral, that's gonna be an aileron, and then
Okay.
most of the intersections flaps.
Okay, and that doesn't add, the motors you just described don't add a whole lot of weight. So that's good. Okay, thank you.
Someone walk us through the logic of putting that motor in the back of the aircraft.
Sure, I can walk through it really quick. So the primary reason why we decided to put it in the back is so we could put the camera as far forward as we could, built it into the nose cone. If we would have put the motor in the very front, we would have had to integrate that kind of like a Cessna or like a Piper, more of a conventional aircraft. If we did that, we would have had to create a bubble of some sort on the bottom for our camera to look through, or integrate the camera further back into the middle. We could have looked at doing that, but we wanted to integrate it into the nose cone. Originally, when we were looking at designing this, we wanted to be able to point and shoot at a GPS coordinate, potentially track it. So having a large field of view is desirable. Now we're kind of transitioning that. We may still have that as a feature. So that's why it stayed up there. But if we purely wanted to look down and we're always going to be flying straight and level, we could have moved it further it back into the fuselage. But we put it as a pusher just to separate the two systems.
Two more quick reasons. Another one was to get clean air over all of our control surfaces. We've seen some funky effects in our tails before where we didn't have the leverage that we wanted. And then a third reason is since we want to have that camera up front, if we have both the camera and avionics and the motor up front, which are two of the heaviest systems, then we're very nose heavy. And we're gonna, have to distribute that weight backwards. So we thought that would help to balance it out pretty evenly.
I have one more.
Okay, so you guys just talked through the advantages of putting the motor
Yep.
back there, or some of the disadvantages.
So the biggest disadvantage is our ground clearance, potential prop strikes. And that's one thing that we tried to mitigate or use to mitigate that was that Y tail, using the vertical stabilizer to prevent it. As far as stability goes, lateral stability, there's actually a slight benefit of having it in the back. With the yawing like a Dutch roll, there's actually like very marginal benefit of having it in the back. So we weren't too concerned about stability wise. The other negative that we can see from it is the actual resistance of the wire that we're going to have running from our battery pack to the motors. We're going to have some losses there, just due to internal resistance of our wires. As far as that goes, that's kind of all we've found. Do you have any additional ideas? Because we'd love to hear them if we missed some.
Not manufactured perfectly, you're gonna get a large number of center of gravity.
Okay. Pitching moment or?
Depends on what direction it's all.
Oh, okay. Gotcha. Sweet. We'll do Audie last question and then move on.
Yeah.
Yeah, I was gonna ask, how exactly you're planning on testing for lateral stability? Because I don't think X-Flyer does a very good job at testing. Because they just launched longitudinal. What are you using for lateral?
So we've done longitudinal static stability. Within X-Flyer, they do have dynamic lateral stability. They have longitudinal and lateral stability. So right now the plan is just to do that through X-Flyer. That's kind of step one. After that, we don't really have a test plan for the lateral stability.
Can you test for a tip stall limitations?
I think we'd probably have to do that in CFD, would be my guess, or in a wind tunnel, something like that. So that's definitely something that we should probably look into. Do you have any recommendations or anything?
Nothing.
Okay,
I have a recommendation for tip stall
okay, yes.
because X-Flyer gives you the lift distribution on your wing
Mhm.
at every angle of attack.
Mhm.
You can see the local CL on your wing for every angle of attack.
Yep.
And you can see the CL at the tip of the wing.
Mhm.
Now you know your airfoil, you know the CL at the tip. So you know the stall angle of the airfoil, so you can predict the tip stall is happening through the distribution.
Oh, okay,
in X-Flyer.
okay,
That's a
yeah,
good-
need to do that.
You don't even have to go to CFP to do that because pulling lift distribution from CFP is way harder.
Okay,
So you can probably try to get an estimate of it from X-Flyer.
Mhm.
And this is probably the easiest way to do it.
okay. Yeah, we'll definitely make sure to do that. Thank you for that recommendation. That helps a lot. Okay, we're gonna move on to our airdrop section. I'll let you take over here.
Okay, so my name is Evan Cam. I'm leading the airdrop team this semester. So just really quick, go over some of the requirements. So competition requires that we safely deliver the payload to its like respective target. And that safely is kind of just a judgment call by the judges that are standing there. So that are stay on the safe side. And we need to be within 15 feet of the target. It's dropping from an altitude of 100 feet. When it's falling, it cannot have any sort of propulsion or like propellers or any of that. And then when it lands, the judges have to be able to remove the water bottle with no tools. So this is just kind of a quick overview of what we're in charge of. So we need to somehow incorporate our mechanism into the fuselage. We need to drop the payloads, and we need to be able to drop them in any order. Looking at the payload, once it drops, we need to somehow deploy a parachute, and we need to design those parachutes as well. Okay, so in the fuselage, we decided to go with the revolver mechanism. And the reason for this, or I guess really quick, we have 9 inches of diameter that Corey and the airframe team are providing, and 16 inches of length. So the reason we decided a revolver is because the center of gravity doesn't shift longitudinally. So from like the tip to tail, center of gravity would not change. And the payloads can also be dropped in any order. So that's the main reasoning. And then I'll get into kind of why the revolver shape looks how it does. And also, if you can kind of tell on like the back side of that bulkhead behind the water bottles, there's like just some gears. We would put like a stepper motor maybe back there, and that would rotate the revolver. And then inside those bulkheads are also some ball bearings. Okay, so this kind of explains why the revolver looks the way it does. So, and this is also how the payloads would drop from the fuselage. So we have 2 mechanisms that we're going for right now. The electromagnet system. So the water bottle and its encasing would be held up by like permanent magnets, and that's shown by the blue and red little bars on the left. And then once it's time to drop the payload, we would turn on an electromagnet that's shown in the middle with the 2 blue bars, and that would have like a repelling force that would like break it off of its magnet. So that's the first system. The second system is more just like mechanical servo motor system. So it would just be held up by a servo, and then when it rotates 90 degrees, if you look at that thing that says top view, it would kind of just like slip through the crack and fall. So those are our 2 designs for dropping the payload. So the payload itself is the water bottle, and it would fit inside of this, what we're calling a pod. So this pod is kind of split up into 2 sections. The payload section is shown on the right in dark gray. So the water bottle would sit in there. And then in light gray, that's like the parachute deploy mechanism. So basically what we're planning on doing is dropping the parachute, having a drogue chute open up immediately. And then once we get like closer to the target, then we'll like release that lid, and the drogue chute will pull out like the actual parachute to slow us down and safely land on our target. These 2 sections connect with just like a thread, like a water bottle cap. And then the slot in the lid is just for that drogue chute, so that when that lid opens, the drogue chute can just slip through that slot and pull out the actual parachute. Okay. Going into parachute design. So right now, this is our initial parachute that we made. We ran into some trouble trying to think of how can we make a parachute that's like a hemisphere. So to do that, we'd have to cut like, it's hard to describe, but you can't do that out of just like a flat piece of material. So that's kind of the issue that we're running into. So for right now, we're testing with just a flat octagon that we cut out. And then we cut a hole in the middle, and we calculated it to be around like 40 inches in diameter for the speed that we want to fall at, which is around like 10 feet per second. So different things that we want to test or maybe ask you guys about is, should we only like tie strings to the outside, or should we have strings on the outside and the inside so that it looks more like that orange and black one on the right? Or if we only do it on the outside, it'll look more like that red and gray one. And this can be testing. If you guys have any input, we would love to hear it. Yeah. So you can either say it now or wait till the end, one or the other. Oh, is that, oh, sorry, I thought that was from earlier. Yes, Charles, Seth. I don't know if you forgot to, I think you might have forgot to unraise.
Okay, sorry about that.
Oh, no problem. Okay. Let's see. So, oh, all right. So this is kind of how two different mechanisms that we're looking at for when we want to release the parachute and have the drogue chute pull it out. So we have an electromagnet system and a pin system again. So the electromagnet system is pretty similar to how it would fall out of the aircraft. So on the red and blue magnets, those are just like permanent magnets that would be holding it shut. And then once it's time to release that parachute, the electromagnet would kick on and prop that lid open. Another mechanism is just a simple servo mechanism that pulls a pin. And then the drogue chute would provide enough force to pull the parachute out, or if it doesn't provide enough force, then we would just like spring load the hinge. Okay, I'm gonna pass it off to Vanessa, and she's on the airframe team as well, or airdrop.
Hi, I'm Vanessa. I'm just going to explain the schematic for the parachute release mechanism really quick. So it's very simple. The payload is going to be attached by a wire to where the avionic battery is there. And then once the payload is released, that wire will pull out and it will trigger a 555 timer and will delay 2 seconds. And after that 2 seconds, the electromagnet will pulse for 2 seconds. So something that we need to figure out is how long that pulse actually needs to be. Right now, I just estimated 2 seconds, but maybe it could be shorter and we could save energy. And also we need to figure out how much time after the payload is released that we need to start the timer. Okay.
You have another slide.
Oh wait, I actually do.
I'm a little confused about which parts of this circuit are located on which physical object.
Okay, so everything is on the payload except for the avionic battery right there. This is just a representation of the attachment to the battery. The rest is going to be on the payload. Does that make sense? Well, and also this. So this is the electromagnet that will pulse and repel what's attached to the parachute. And this is a little model of the magnetic field. And then this is the force. So I just included that in the simulations that later, when we figure out how much force there will be, we can calculate that easily.
So also, Charles, what I'll say is when the pods are like in the fuselage, there'll be like an alligator clip or something where they're attached to the avionics battery. So all that's charged up. And then once it drops, it just slips out of the connection. And then that'll like start the timer.
Thank you.
So then,
It's not there.
that's okay. All right.
So this is kind of the timeline for what we're hoping to get things accomplished by. We really need to get some testing in for this so that we can create a trajectory, see how our parachutes behave, things like that. Yes, Charles. A lot of Charleses.
I was wondering why is the payload mechanism so complicated?
Why is what so complicated?
The whole delivery mechanism.
Yeah. Like delivery in terms of like the parachute and how it gets deployed.
Yeah.
Yeah. So basically it's really hard to hit that target. And if we don't hit that target, that's like a huge loss of points. So if we just like dumb drop use like a dumb drop where the parachute just deploys, then any sort of wind is like very likely to push us off of our 15-foot radius to hit that target. So we want to keep it as simple as possible while still being able to hit that target. But it's kind of basically we have to hit that sweet spot where it's like simple, but good enough to hit that target.
I can jump in here really quick too. So one other comment to make is based on our GNC path planning that we're doing. We're trying to set our system up so that we, if we have any wind conditions at all at the field, we're going to be flying directly into the wind so that we don't need to worry about our crosswind. However, that's something that we're going to have to manually input into the system, or maybe we can live time update it. But there's going to be some variability there. And then there's also going to be some variability in like how we pack our parachute, for example. And so there's certain unknowns and uncertainties that we cannot model into our actual payload trajectory. So the idea behind creating an actual deployment mechanism that activates after a certain time period is to help reduce that, reduce how much it can be magnified by. The closer we can drop to the ground, the better. But the more simple we keep it, the better, for sure.
Yep. And then
So you'll be dropping from a preset altitude.
yep, and we would find that by testing a lot.
We have a floor. You can't go lower than 70.
Yeah, and we can't go lower than 75 feet.
Yeah, I'll jump in here real quick. I'm Andrew. Basically in the rules, so the way it's being scored this year is that we get 20% for each water bottle that lands within 15 feet of the target. And if it lands at 16 feet, we get 0 points. So we have to hit all of these within 15 feet 100% of the time. And the minimum altitude we can fly at is 100 feet. And so then the maximum wind condition they said that we have to be able to operate in is 15 knots continuous. So basically for us, that creates a problem where if we deploy the parachute immediately, within probably 40 feet, I think we calculated we would be off already more than the 15 feet. So there's almost no way we can guarantee that it would hit the target if we pull immediately. So we have to do a timed release like this.
So do you have a winds aloft estimator?
Yeah, we do. We have a weather station on the ground.
Oh yeah. So we just ordered some tools that are going to be estimating the wind for us. We're not sure if we can update those, like what rate, if we're going to update it before we fly, or if we're going to be able to update it in real time. But we're working on that.
That's not what I was asking. I'm talking about an estimator in the autopilot.
Yeah, so GNC is going to talk about how we're doing the path planning. But basically, we should know airspeed with pitot tubes and also our ground speed and GPS and all that, so we can calculate the optimal trajectory. But there's just going to be some variability in that, so we don't know exactly where it's going to land, basically.
Okay.
And if there's no other questions, I'll pass it off to Diego. Okay. Thank you. What?
It's another time.
Hello. I am the software systems lead, the object detection, localization, and classification lead, and the software core lead for Purdue Robotics. And I'll be talking a little bit about that today in our PDR. So we're going to go ahead and get started with our ODLC. So what does ODLC do? You can imagine you have this UAV now, and we have to drop these water bottles onto these targets, which are, composed of several characteristics. We have the shape, the letter, and the colors of the two, and we have various combinations of these. And we have to drop the water bottle exactly on that target. So there's some emphasis there on kind of the accuracy. So we have to have some system that's going to be able to detect these and resolve their GPS location so that we can drop this water bottle on there. So before we get into any of the nitty-gritty software, let's talk a little bit about what the data and the hardware is, what's going on here. So you can imagine we have kind of this raw GPS data that's going into our flight controller. And we have our Jetson Xavier NX, which is our kind of ODLC computer that does all this computation. It receives its GPS data. At the same time, it's taking images from the GoPro Hero 10, sending these over. Remember, some magic happens. We get these detections and images. We send them over this awesome transmission system we'll talk about later. And then we're at the ground for monitoring, manual annotation. They go all the way back up. We decide what we want to choose, and then we send it over to a Raspberry Pi, and that's going to choose what water bottle we're dropping to what GPS location and all of that stuff, right? Excellent. So what is this magic? I think that's like the big question. What do we do to actually be able to detect these targets? So it doesn't matter if we're using a classical algorithm or a learned algorithm. We need data. We need data for testing, and we need data for potentially training, right? There's a lot of characteristics, and we could spend the whole year kind of manually making these targets, and we show up at the competition with only like a big stack of cardboard to show and nothing else. And you can imagine this number kind of explodes when you consider the font and the size of the targets, right? So what we do is we synthetically generate these targets. Lucky for us, this is a bit trivial, right? They're not complex as like humans, for example. It's just targets. So we can kind of procedurally generate these shapes and then put the letter on them and then color them as we need. But, you know, there's a problem here. You can even see that they look pretty real and they kind of, you know, they are targets, but they're not as realistic as maybe these on the left, right? So every year we try to kind of come up with this magic method of how can we turn the synthetic target into a real target? How can we map that function that just says, make it real? Kind of in the top left here, you can see we have a synthetic target and a real target, and it's kind of missing that special something that makes it a real target. Last year, we tried using CycleGAN. CycleGAN says, give me a bunch of real targets and give me a bunch of synthetic targets, and I'll figure out how to map the two of them. The problem was we didn't have enough real targets, so it didn't work. This year, with new innovations happening, maybe you've seen like the text to image or image to image kind of trend going on. A lot of the open source community has recreated that in kind of an open source environment. So we can take advantage of that to do this kind of transformation using all these pre-trained models publicly available. If that doesn't work, we're also trying Pix2Pix. Pix2Pix is like CycleGAN, but instead it says, give me image pairs. So give me one image like this one, maybe this is a bit exaggerated, and give me a real image like that, and I'll try to map the function there. So it requires a little bit less data, but it can still learn the function. And there's also pre-trained models out there, so we can just fine tune it a bit. Remember, the whole goal is we don't have a lot of real targets, so we're looking just to fine tune something that's already most of the way there. So we have the data. Maybe it's real, maybe it's not so real, but we have it. We get the input image. We do kind of a sliding window of it over the image. This kind of cutting it up is maybe a simplification. And the reason we do this is we don't want to be resolution specific. So if we say it should be 5.3K, then when we kind of scale up to different resolutions or shrink down, it doesn't work as nicely. So we have this kind of sliding window so that we're kind of resolution agnostic. We batch all of these up. So you have this big vector of all these kind of chunks, and we put it through the magic, the detection and characterization algorithm. We use deep neural networks. Why don't we use classical algorithms? It'd be much simpler. They're just shapes. In the past, we've used classical algorithms, and we get 60, 70, maybe even 80 sometimes % accuracy. But you have to remember, there's only 5 targets we need to detect. And if we miss any of them, we lose a huge amount of our points. So we need something that can generalize to a massive amounts of diversity in our targets. And you can't really do that when you have an engineer tuning a bunch of parameters on some classical algorithm. This is iteration 1 of kind of the deep neural network architecture. You have a model over here. We've always had great success with YOLO, and it's the open source community has created very small and modular versions of this. And it detects kind of where the target is. And it says, find me the target and kind of crop out where it is. We have a non-max suppression and crop layer, just gets the target. And then we do characterize this target. The whole point being that we kind of want to connect this end to end. So you can add a kind of a skip connection to go over this non-differentiable area and connect the two. And that way, when you're doing back propagation on all these loss functions, it goes all the way back to the very start. So let's zoom into this characterization a bit. So why do we have this kind of shared head? You can imagine that when you're doing alphanumeric, shape, and colors, you have to learn something about what a target is, what is a shape, what is a color. The neural network doesn't know anything. It's stupid, right? You have to teach it all this stuff. And so it learns all of this, and this, the whole point being that it'll learn something and it'll keep all that general knowledge here in this big shared head, and it'll just specialize in these small heads. And then all the gradients propagate back through the entire network. And so it has this very general understanding. In terms of data we need, the data is more or less our synthetic data, right? We have these kind of chunks, images filled with targets, and we've labeled them all. And this is very easy because we synthetically generated them. We know what letters are on them. We know what colors we've made and what the shapes are. So we have all this data and we have our network. There's a problem. Like I said, this is our first iteration, and there's some pros to this. Because we have the shared representation, it means the network is faster. We don't have to have a bunch of networks relearning what a target is. And we just have one training session, and we just have one annotated training set, right? Great. The problems are multitask learning and optimization is hard. There's a paper by you and others called Gradient Surgery for Multitask Learning, where they point out some problems when you're optimizing. Sometimes your gradients are going in opposite directions and their magnitudes are weird. And it just causes you not to reach your optimal and kind of reach this saddle point. We could use their proposed solution, but it just adds some more complexity, right? Also, weighting the loss functions. Like I said earlier, we have 1, 2, 3 loss functions, and maybe even the object detection loss function. All of those could be weighted equally, but maybe our training isn't going super well. Maybe we have to weight them, and that's really just trial and error. And you have to train this whole big network again. You're using a lot of time. There's a strong bias towards the synthetic data. This whole thing is trained on one annotated data set that's synthetic. So it has like a very strong bias. So maybe we get to the real competition and it doesn't perform well. And lastly, it's not easily explainable. Imagine everything is predicted correctly, but not the color. What happens? We have no idea. If you go back a little bit, all you're going to have is a big dense tensor full of floats. There's no real idea. Maybe this shared head wasn't big enough. Maybe we didn't have enough color data. Maybe the color head was not big enough. It's not explainable. So how do we solve all of these and kind of keep maybe some of these pros? So do we need to do inference quickly? The purple region is the only region there's going to be targets, and maybe that orange dotted line is like a optimistic flight path. But the majority of the time, we're not seeing any targets at all, and we know that. So why not just process the images that intersect with this purple region, and we forget about the rest of the area? And by doing this, we can spend all this time processing, and we just have to spend a little bit of time taking the pictures. That happens concurrently, but the idea is that we don't have to worry about inference speed as much as if we were doing searching and we had no idea where the target was. So from our second iteration and our final kind of decided network, this network says, let's not do the multitask, let's specialize everything and make it much more explainable. So our first network detects the bounding boxes in the shape. You imagine you have kind of, you're looking for the target in this image, you have to have some idea of what the target looks like. Will it like triangle, square? And so it takes care of that. We have a unit does segmentation. Imagine you have a picture of a target. You want to separate out the background, the target, and the alphanumeric. That's what the unit does. So you basically come out with 3 separate images. That's a bit of a simplification, but you have the background and then you have a target and then you have the alphanumeric. All are separate. And what does this do? It lets the alphanumeric not care about what our competition is or what targets are or any of that. All it cares about are what are alphanumerics. And that's a really easy task to learn. And for color, it doesn't need to know about the competition. It just needs to know what RGB colors or what labels or color names. And by doing this, we've solved most of our characteristics by not caring about the competition, made it much more explainable. For example, if color is wrong, we can check, we can go back to the output of the segmentation. Did it segment properly? If it did, it's in the color module. If it didn't, it's in the segmentation module. And now we can train on some open source data. And now only our first 2 networks are biased on these synthetic data. And so that's our kind of proposed architecture. It also works well because we can kind of parallelize the work. But that's that. Is there any kind of questions or comments on any of that? Feel free to unmute yourself.
Hey, I had a question. How long do you see each target for? How long is each target in your field of view?
It should be in our field of view for maybe 2 or 3 seconds, but we take about 60 frames per second. And because we know those targets are only in that region, there's no point in sampling kind of those that stream versus just processing all of them at once, right? And because we're taking 60 frames per second, you can imagine some of that motion blur is not really there because we're taking images so fast.
So are you using the fact that you have multiple shots of the same target and thus, these images are correlated?
Right,
Are you-
right. So maybe, I don't think we have time to get into that today, but you can imagine after that, we have kind of this vector of all the predictions. And at the end, we kind of look at the frequency and also some other factors to weigh the decision of what are our final guesses. And in a second, I'll also talk about for software core, we have some annotated or manual labelers on the ground. And so their decision, plays a part in that as well.
Perfect. Thanks.
Yep. Anyone else? Yes. Oh, yeah.
So I have one question. To go back to this.
Let me know when.
Yes. Yes. So you mentioned, for instance, all the calculations can be done on the left side of this case, where the targets are.
Sure. Yeah.
So how are you going to map the GPS coordinates of those targets while the calculation?
So maybe we can talk about this more, but you can imagine our system is very concurrent. So at the same time, we're getting camera images, we're also getting telemetry, and we're also doing a whole bunch of other stuff. And so we're getting telemetry all the time. And so when we take a picture, we have a timestamp for when that picture was taken, and we have a timestamp for when the telemetry was done. And we do kind of a search to find the most ideal one and then resolve the GPS like that. Charles, what were you saying?
I was going to suggest that you could test this system almost in a graduated fashion to go from a very simple system that takes the camera records and runs it through your system and guarantees that it works. And then you could actually take it and I don't know how you would support it, but you could get it at some altitude and make sure that you're able to reconcile the objects and to get the resolution you need to not only get the camera working in sync with the system, but also to train the system as you go.
Yep. Yeah, definitely. One of the things that's great about synthetic data generation is, let's say we're out on the field and we're testing and we don't detect the squares. We look back at the synthetic data generation and we say, we didn't detect the squares. What's wrong with the squares? It turns out not all squares are perfect. In our synthetic data generation, for example, we might have only created perfect squares. And so in the synthetic data generation, because we control it, we now make the squares slightly imperfect. And the neural network understands squares aren't perfect. And by doing that for all these different types of characteristics, we introduce a wide diversity into our data set. And it just learns in general what these shapes are without constraining it. Any other questions?
How'd you come up with your 640 by 640 resolution requirement?
The 640 by 640. So object detection models, maybe it's just it's just common to have 640 by 640. There's also 480 by 480. These are just things that are common in kind of the open source community. What's great about this is because if you follow along with that open source community, you can use kind of pre-trained networks that they have and then just start training off of those. It's been proven many times in research that by doing that, you actually increase your final accuracy, even if the previous network was trained on something completely unrelated to what you are training on. It's really cool. Any other questions? Okay. So last year, you can imagine that you have these train weights and it's a file, and now you're going to fly the UAV. You can't really just, I don't know, print these out and stick it on the plane. You have to have a system to support it. So last year, a few individuals kind of just worked on this, but this year we have a whole team for this called Software Core. So they build the system that these models run on. And on top of that, they work on fault tolerance and just making everything work, kind of the architecture of the system. Going back to kind of the flow of data, you can imagine that inside of our Jetson, maybe it's a happy world. Nothing bad happens because we control a lot of it. but as soon as you come out, you have all these areas for points of failure. So imagine one of the biggest of these being the transmission. Let's say, even though our transmission is great, let's say it starts fluctuating. At 1 second, we're getting 50 megabits per second, and then something happens, and the next second we're getting 1 megabit per second. We're not doing anything. So how do we make sure that our images and detections and our telemetry is still getting to the ground? So kind of one of the things a lot of us learned in kind of introductory courses is the priority queue. So maybe I want to get my full images down importantly because they're high priority and my system telemetry is low priority. I can make a priority queue. What's wrong with the priority queue? The problem is when our transmission rates dip down, we're producing data so fast that the front of our queue is going to get clogged up with all these high priority full images that we're never going to even be able to send the system telemetry or even our detections. And those are still important to us. So we'd like to send system telemetry, but at the same time, we'd like to, prioritize our full images. So how do we do this with something a little more complex? So we use something called weighted fair queuing. This is the same thing your CPU uses and your router uses to be able to send or decide what process to run or what packet of data to send. We do the same thing. Weighted fair queuing more or less says, assign a weight to each of your priorities, and that's how much bandwidth is going to be allocated to each of them. So by kind of assigning a finish time to each of our pieces of data, we're able to kind of simulate that. So now our full images are still prioritized. They're getting half the bandwidth, but we're still receiving the system telemetry and the detections because they have the other half, right? And we can kind of tune these in practice, but it solves that problem, right? So we've handled the problem where transmission rates dip and they go up and down. All right, what happens if they go out for more than a few seconds? There's RAM in a computer and there's memory and it's limited, and you have a bunch of full images clogging up this queue. At some point, your process is going to get killed because you ran out of memory. So how do you handle this? We have lazy queues. Lazy queues say, don't put everything in memory, just get a little bit of piece of metadata to recognize what that data is, put it in memory and put the rest on your disk. Once it's on your disk, it's out of memory and you're not clogging up all that space. And that way, you're not having to worry about your memory overflowing. And as soon as it comes out of the queue, you can just pull out the body of that data, the big image, for example, and then send it to the ground station. By doing this, we can lose transmission rate for most of the mission and still not run out of memory. So this is great. What's even worse than this? What's worse than transmission being lost? Let's say power just goes out or our whole system goes down for some unknown reason, right? It could happen. What can we do? We do persistence. Persistence says we want to handle the fact that if your system goes down in between a write operation or the whole thing turns off, it's all still there. And so we have a SQLite database and an object relational mapper on top of that structures all our data onto the disk, makes it really easy to recover on the chance of a power failure or complete system shutdown. This is not only great because of that, but also it means none of our data on board will be corrupted. Atomic just means it either writes or it doesn't write. So in this manner, if we lose power for a second, we're able to recover our states immediately with no problem. All right, we solved the problem of fault-tolerant transmission. Well, what do we do now? It gets to the ground station, and how exactly are we doing this annotation? We do distributed annotation, and I'll explain in just a second. We're able to publish these messages to a RabbitMQ message server. These are consumed, or the queues in this server are consumed from a Django web instance, kind of like a web application. It opens WebSockets to several annotation or kind of instances, which are just annotators sitting at computers with this kind of web page popped up. And a little more technically, maybe, each WebSocket binds to this queue and it just consumes from it. So every annotator gets a unique image. It sends down the full image or the cropped images, as well as the prediction. So the annotator can, detect or highlight new targets or fix predictions. If two annotators annotate the same image, we check for a GPS location overlap. And then that way, as soon as all the annotators have finished, we have kind of this intersection of all their annotations and send that right back up. So that's the distributed annotation. The distributed part being we can have as many annotators as we want and it works well. So like I said before, we do persistence. this is maybe a simplification of what we do, but we record every single piece of data from the system telemetry, like CPU usage, to the Mavlink telemetry, like our heading, all the way to our cues and our videos and our frames. And we do this for two reasons. One reason being we get some really great testing capabilities. If we record everything during our mission, we're able to play all this back in testing. And even if we're testing in a room somewhere, the system's going to feel like it's in the air. And also we get some monitoring capabilities like Grafana. You can imagine it gets to the RabbitMQ server, it goes through a Django ORM, and it gets saved to our database. And we have Grafana that's just looking at our database, and it's looking at the latest rows. And by doing this, we're able to show telemetry for every part of the system, as well as its status. And because this is connected to a router, and anyone can connect to this router, anyone can see this dashboard on all their devices. This makes it great for monitoring with multiple eyes and doesn't limit it to one computer. And the monitoring in general is great. But on top of this, we also do live streaming. So we have FPV cameras on board the aircraft, which are sent down to an FPV receiver. We'll talk more about the actual hardware later in the presentation. And these are sent to kind of a live streaming service we've stood up on the ground. And that way, anyone on any device can see the actual live footage from the aircraft. This is not only cool, but it's great for debugging and monitoring, maybe catching something that we couldn't have seen from the ground, right? Lastly, it's unfortunate we didn't get to talk about the full system, and we just got to talk about some components of it. But in terms of testing, we do the simple things. We do unit and integration. We also test on the hardware we're actually going to use. We have the Jetson as our automated runner. We do this because we don't want any surprises. Testing on my laptop versus testing on the Jetson might reveal some surprises. We don't want surprises. We do the playback testing from before, making the system feel like it's on the aircraft when it's not really. And then there's flakiness. Flakiness means non-determinism in testing, happens all the time. So we have nightly tests. So not only on every code change do we run the test, we run it at night too to catch any non-determinism in our tests. So that's all for our system. I'm going to go ahead and open it up for questions if anyone has any comments, critiques, or general questions about the system or what Core does.
Just a couple more quick questions. The transmitter on the aircraft, is that located on the front or the back?
Will, I'll actually ask you to hold that question.
Okay.
We'll talk about it in a second in more in depth. I think you'll get a better picture of that. Yep.
Okay, sounds good. And then where's the ground control station on the map with respect to the target area?
Sure. We are kind of right there. I'd say between maybe the green and the blue blocks.
Got it. So you'll be flying toward sort of half the time and flying away half the time.
That's right.
Okay, thank you.
So, right, transmission, you'll hear later, is pretty fault tolerant itself in the hardware, but anything can happen. Someone on the ground could literally just knock over the whole antenna, and that could be our failure. So we prepare for that. Any other questions? No? So I'm going to go ahead and pass it off to optics and avionics, and they're going to wow you with our solutions for that. All right.
All right. I'll play it. All right. So we are the optic and avionic team. It's a competition overview. We don't have time for it, so I'm just gonna skip it really quick. So we are working on three key areas. First one is avionic core. It's a very integrated computer stack that holds all our avionics, including like the flight computer, power supply, and other stuff that you might need. An optic system is basically camera for the entire computer, and the power delivery is the power supply, and we need to figure out how to make the battery and monitor all the batteries for the aircraft. Okay, so for the avionic core, we want to make a very robust and flexible platform for all of the avionics. All the modules will be interconnected by controller areas network, which is a very industrial standard. It's very robust and it's really good for our application. One thing really good about our design is that it is very flexible. We are gonna be putting like only 2 modules in for phase 1, which is the power distribution and monitor system. Another one is our autopilot computer. Down the road, we will be adding more modules in, and we will like do a lot of other stuff. The autopilot computer is a custom carrier for the Cube O-ring. Cube O-ring is a flight computer that we are using. We are gonna break all the connectors on the board into a single connector. So all our ground team, all our sensors will be connected in a single cable, and the ground team will able to just connect one single cable in, and they'll be done for the installation. This is the mechanical design for the thing. We are still gonna need to figure out how to make the Cube O-ring happy with our power supply, but this is a general concept of the design. This is just the design constraint for the autopilot computer. It's a schematic. Next one is the power distribution and the monitor system. This is a power supply for the avionics system. You will take a special battery. You will take a standalone battery aside from the propulsion, just to power the avionics. It will take up to 8 cell input and monitors all 8 cells with like voltage and currents. It has 5 really high efficient DC-DC power channels. It will have 12 volt, 5 volt, 3.3 volt, and 2 adjustable power output just in case we need something else that we wouldn't consider right now. The module will be monitor all the propulsion batteries with a separate module in the back of the aircraft, and it will monitor up to 21 propulsion battery cells and current up to 120 amps. We won't be needing that much, but it's nice to have flexibility. And the board also will have like self-contained management system, so the ground team will be able to control it on the ground, just with their phone or tablet. And for the motor battery, the propulsion battery, for now we are using 2 large LiPo batteries. Though they're really good for power outputs, but the issue is they are not as dense as it can be. For the future, we want to look into better solutions that are more aimed toward density, so we have better flight time, and to make and we don't really need that high peak power, but it's just good high for now for testing. The plan for the team is for the avionic computer, we already have the schematic built mostly done, and we are finalizing the design. We are aiming to get a fabrication in like 3 weeks. For power distributions, we have the general idea done, but more prototyping. We're still actually making those things, and we are expecting to have fabrication in 6 weeks. For propulsion batteries, we are using off-the-shelf LiPo battery for phase 1, and we are researching a more advanced Lion solution for improved performance. So any questions with avionic parts? Yeah.
So like things probably related, but could you go more into detail of how you actually chose your batteries and how you thought like how you came up with numbers for your current draw? Is that related to like how much power is required?
Yes. So I'll go back to batteries. We are expecting like 5 minutes of takeoff time, which the motor will be running at peak power outputs. Then afterward, the motor will be running at around 60% for the cruising. So we will have a estimated power that is needed for the entire missions, and we are basing our capacity based on that. Right now, the 2 16,000 LiPos doesn't actually quite meet our requirements, a bit short, but it's good for testing in case we need it. In case we can, no, it's good for testing, and we are like upgrading into LiPo battery, but that will take some time. Yeah.
You said there's more batteries that we look into, which is probably better for you. So
yes.
Like some ideas on what can be better.
Yes, so LiPos are really good for power outputs, but they are not really dense enough for like weights. We want to have as long as flight time as possible, so we want to look for more dense solution. Lion is really good for density, but it's not good for power outputs. But the issue is you need a large enough battery pack anyway, so the power output adds up and it meets our needs already. So the only issue with Lion is it is not really for hobbyists. You can't really buy a hobbyist pack that we can just use. So you have to figure out how can we make those packs in house, or we had to like commission a pack from like a company or something. All right. So
this is James Goppert. Where is your magnetometer located, and are you using external magnetometer or internal?
That'll be inside of the flight computer. There'll be one inside, and there'll be another one on the GPS. The GPS will be connected to the board externally on the outside of the aircraft.
Where's the GPS located for the external magnetometer?
On top of the wing base.
Okay, is it away from any electrical currents?
There shouldn't be any because the motor is really far back and all the avionics are like really front forward. So the only thing it's right above the airdrop bay, which is like nothing going on. So I think it's pretty good.
You had some electromagnets in the airdrop bay, right?
Yes, but it should be weak enough to not matter that. And we have like carbon fiber shielded, so I think it's gonna be fine. You'll figure it out.
Yeah, double check.
All right. Any more questions? All right. Up next, we'll talk about the optics.
Hi everyone, my name is Cameron Johnson. I'm a member of the optics and avionics team, and I'm just going to be discussing the optics side of the optics and avionics team. But before we get into actually the cameras that we decided to choose on, we have to get into what we're actually trying to do, right? So as you saw from the ODLC presentation, our goal is to basically detect and classify targets, right? And we know that the runway has a minimum, has a scan width of about 70 feet long, or 70 feet wide and 360 feet long, right? So we need to be able to have cameras with the proper field of view so that they can actually scan the full 70 feet so we're not missing any targets. Also, we also need to have a high number of pixels per foot because as you can see in the diagram, 15 pixels per foot isn't very ideal. It's very blurry, it can be very difficult to actually detect the object. And compared to the 60 pixels per foot, which is clear and defined. And essentially, we want to make it easy for the ODLC team to run their algorithms. We don't want to give them bad data. We want to give them as much good data as we can. We also need enough frame rate to match the aircraft speed. So we have a phase 1 camera, which is our GoPro Hero 10, and it has a scan width of about 94 feet. And the camera pixel structure is about 24 megapixels. And that'll result in about 60 pixels per foot. Now, the thing with the GoPro, because it's operating at 60 frames per second, it has incredibly high pixel structure, and we're only using USB, which has a max of 5 gigabits per second. And that's way too much data to live stream. So what we're doing is we're using a stop and record system. So pretty much we will record for a certain amount of time, and then there'll be a small delay in there. The reason why we decided to do this over live streaming is because we want as much resolution as possible, right? Like I said before, we want to make it as easy as possible for the ODLC team to run their algorithms. So rather than going with a smaller camera and sacrificing resolution, we feel that we can time it perfectly with the runway. That's our phase 1 camera for the GoPro. However, our phase 2 camera involves multiple cameras. We call it the multicam project. So recently we were sponsored last year by onsemi. So we have 4 AR820 cameras. Now this camera pixel structure is 8 megapixels, 3848 by 2168. However, we plan to have 3 cameras on a bracket, right? And so this will result in triple the amount of pixels, right? So it actually would equal 24 megapixels total, but instead of having it, so if you go back to the pixel structure, you have 5,663 horizontal and 4,223 vertical. Instead of having more in the vertical, you're essentially just making a strip of one long horizontal pixel structure. The color filter array is RCCB, which is red, clear, clear, blue. We're going to be operating at a frame rate of 30 frames per second. And instead of using a data rate of USB, we're going to be using a 4-lane MIPI CSI2, which this can achieve us up to 2.5 gigabits per lane max. So we can actually get up to 10 gigabits per camera, which is plenty of bandwidth. And also with the actual camera structure on the bracket, there's going to be about 2 feet of overlap, and you can see in the diagram. So when we get to the actual structure of how the camera is set up and how we're going to design this mechanically. So we know that the lenses are going to be 21 degrees field of view. And with all 3 cameras combined, this will give us an effective scan width of about 111 feet. And this will achieve us about 104 pixels per foot. So compared to the GoPro, we're getting just under double pixels per foot, and we're getting much more scan width. And this allows for more variability and error. Let's say that we are drifted off to the wind, we're not perfectly aligned with the runway. We want to be able to have as much safety precautions as possible. It's going to be a GSML2 connection through a celerizer, decelerizer. And since they're angled cameras, we will need to dewarp them. However, we will be able to know the transform from the IMU to the cameras at all times. So we can easily dewarp those. And so in the diagram, you can see that theta equals 180 minus the HFOB. That's pretty much just the mechanical design of we want these cameras to be angled at this specific point so that they perfectly overlap with each other with that 2 feet of overlap. So this is just kind of an overall performance comparing the GoPro Hero 10 to the multicam solution. So with the GoPro Hero 10, the overall resolution pixels per foot, it meets the requirements. Obviously 60 pixels per foot is not bad. However, it could be much better. Same thing with the scan width. The GoPro hits about 90 feet of scan width, and it meets those requirements. However, the GoPro does not meet the requirements in live streaming video, which could be very dangerous, especially if we are not able to perfectly line up with the runway at perfect times. We don't want to be missing these targets. We have to hit these targets on the very first run and detect them. With the safety critical, the GoPro does have some issues. The GoPro does overheat after 20 minutes and will turn off, which is obviously a problem that we will have to figure out. It's also using USB, which has been proven to be unreliable. It can drop frames. It also doesn't have a very high bandwidth. But where the GoPro really excels is the development time. I mean, we already have the GoPro working. It's a plug and play camera essentially. Now, if we compare these with the multicam project, the overall resolution, like I said before, it exceeds the requirements. I mean, we're getting almost double the amount of pixels. Same thing with the scan width. We're getting much more scan width, and we're able to live stream video. At no point will we ever be missing any targets. We'll see them at all times. Additionally, the multicam project is, since it's using a celerizer, decelerizer, GMSL2 connection, there won't be any drop frames, and it will always get the data through. And obviously there's no overheat problem. Where the multicam project doesn't excel is the development time. We have not developed the project yet. We need to develop and continuously work on it, which is configuring the cameras, making sure the MIPI connections work. So we just need to develop it. So, and that kind of opens it up to any questions and feedback that you guys have.
This is James Goppert again. You mentioned image dewarping. Did you consider just using a camera matrix and just figuring out the pixel location and world coordinates that way instead of dewarping the image?
Yeah, I mean, we can actually probably use the camera matrix. Like we can get that transform from the IMU to the cameras. So we can probably use it that way. There's multiple ways of doing it. We haven't looked into specifically how we're going to do this yet. This was just a proposed solution.
Yeah, I think dewarping might take more time. You don't necessarily need it. So if you can just map the pixel location to world coordinates, it might be the best bet.
Okay, thank you. Okay, well, if there's no other questions, I think we're gonna hand it back off. Oh, sorry. Charles has
So I may have missed that at the beginning. The mission has first you have a survey phase where you look for targets. and then you do your drops. Is there any in the flight planning and in the triggering of the camera, is there any logic that allows you to do a systematic aerial survey with some coverage guarantees as far as being able to image every square meter of the runway without taking too many images and taking just the right number, so that you process the right amount of pixel overall to find your targets?
Yeah, well, so pretty much that's what we plan on doing with the GoPro. Like, we don't plan on having the GoPro on the entire time because obviously there's that overheat problem. So we're only going to be using the camera for the very first pass of the runway because that's all we need, right? So on our very first pass, that's when we detect and classify the targets. After that, we're going to just be using GPS coordinates to drop off everything off. That's only when that's the only time the camera will be used.
But my question was, do you trigger the camera at specific waypoints to get the right overlap in imagery, or you just let it run for a while and then you download the images?
So sort of like I said before, our system's like very concurrent, so everything is happening at the same time. So you can imagine we're constantly pulling these frames from the camera, and then just based off GPS, we find the intersection between the target area in that image, and then we process it. You can imagine pulling from the camera isn't necessarily compute intensive, but the neural networks are. And even if we did process a little more, like some grass, and the intersection is very small, these neural networks are highly optimized and very fast, and the amount of time we're not looking at this target area is large. So we'll probably be ahead of schedule, even with that overflow. But what I mean is the optimization you're talking about of just capturing the exact right images might not be necessary here, just because of the speed of how fast we process.
Yep.
Is there any other questions? Okay, I think we'll hand it off for the transmission.
Hi, my name is Kai. So I will be showing you how we are planning to transmit data from the aircraft to the ground station. So it's this one. There you go. So goals in order of importance. You can see that we want to make sure that everything is reliable. We want to always have a connection to the plane. So that's like the first goal that we want. And the second goal is that we want to get live telemetry from the aircraft. So there's two different methods that we are gonna have. So one is a radio, like a 950 megahertz radio that's just gonna send whatever the aircraft is doing. And the second one would be through the rockets. So it's gonna be a Wi-Fi transmission system that we're gonna use to be able to send telemetry like from the Xavier, and also for a backup link in case the 950 megahertz radio fails. And so we also want to transmit live video or pictures to be able to make sure that we can verify that it is the actual target that we want to drop to. And so like it allows for us to be able to verify what we have. And as you can see from this map right here, we have a runway that's about 2,000 feet long, where we are going to be, where we are going to be the max distance that we will have. And so the red X right there is the tent that teams will be set up in. And so our antenna will be there. And so you can see like our max distance is about 2,400 feet. All right, this one. There you go. So this is our chosen components right here. As you can see, we have the rocket M2s. It's 2.4 gigahertz instead of 5, because we don't need the speeds that high of a speed, and we prefer to have longer range compared to speed. And so you can see that it uses it's not a connector that
it's used by industry. It uses like RPSMA connectors, which means that we can use the FPV market to be able to grab the antennas that we want. So like, for example, in the past, the Omni antennas that we had was good in terms of like 360 degrees, but it was quite flat. As you can see from the bottom radiation pattern right here, this Omni antenna right here is more like covers a wider area. So we are gonna have two on the plane, on the wingtips, pointing downwards, alongside with a directional antenna, which is the radiation pattern you can see above, is basically where we are gonna be tracking the plane with. And so you can see the polarization, like it's circular polarized instead of linear. And like that's to avoid fading and also to filter out some of the noise, because most of the teams that will be on the field with us will be probably using linear polarized antennas, which means that we get half of what half the noise compared to what they transmit. And so yeah, let's see here. You can see that we have already done some ground testing with it. So we went to a airfield where we basically just put it on the ground and just like drove a car to one side of the airfield, and then with coming back with the rockets pointing outwards, like outside of the car. And as you can see, like this is the data points that we have. And you can see that it has been validated to have like for just the Omnis itself, in case the antenna tracker doesn't work, you can see that we have lows of 20 megabits per second, and directional antennas, they have a low of 30 megabits per second at 800 meters. So we will be flying closer than that on average. So we should expect higher speeds as well, but we will need to do further testing for that. So as you can see, like the transmission capability thresholds. So at low transmission speeds, we get basic telemetry and some low resolution images. At medium, we get full telemetry and some compressed images. And at high transmission speed, we are able to send all of the telemetry data that we want, alongside with images and also the backlog of images if there was a backlog of it. Let's see here. So other than just the Wi-Fi transmission, we do have some simple analog video transmission that we're going to use. So the reason why we went with analog instead of digital is because it's lightweight. We do not need to have a constant connection to it. And it's also easy to integrate. And we're going to have 3 different views from the FPV antenna. So one will be on the tail looking forward, one will be at the nose looking forward, and one will be at the belly looking downwards, so that we can see the trajectory of the payload to verify that our calculations are correct when we are doing our flight testing. So it is a nice to have. It is not necessary for the competition. It's just that it's cool. So for the future, so as you can see, like that's what we had for the antenna right there. We plan to put the transmission on the competition aircraft, like on a past competition aircraft, and also to optimize the antenna placement to avoid as much, to help to get rid of the so carbon fiber, it kind of absorbs and blocks the RF signals. We want to make sure that it doesn't block it as often as we want. And also for ground station, we want to integrate the FPV streams so that everybody can like see it on their phone, for example, and see the telemetry data from it as well. And also we need to make sure that it is as simple to operate as possible. So yeah, that's basically it for the transmission stuff. Yeah. Do you guys have any questions? All right.
I do have a question for you, Kyle.
Oh. Yeah,
Oh,
it's insane.
I don't think you'll need your PowerPoint.
Yeah, okay.
The last year, if I recall, you guys had a fund issues maintaining funds.
Yeah.
Did you ever figure out why that was?
So it might be an insufficient amount of power going to the telemetry module, or like we really figured it out yet, but we are testing with new telemetry modules, and those seems to be more reliable than the previous one. So the previous one we were using was the RFD 900s, and now we're using the XV, like whatever, a lot of stuff from Purdue.
So you think last year was not reliable?
Yeah, it was not reliable, and so like we felt like with redundancy in the links. Also with the Wi-Fi, it seems that it never drops in terms of telemetry, like, and the drops are like half a second and it comes back. So like we feel like we are quite confident with this new transmission system that we have.
All right. Hi, I'm Paul Teeter. I'm the product lead for guidance, navigation, and control. And so what are we responsible for? So we have to develop a method to autonomously control and guide the UAV to complete mission tasks. So that's broken down into basically we have to create a flight path, which needs to be, the algorithm for doing that needs to be lightweight. But the flight path itself also needs to be fast because we are penalized for every extra second of time that we spend in the air. We need to control the plane to follow that generated path. We need to correct the flight path to account for obstacles, and by obstacles, those would include the borders of the map as well as other drones, because we're going to be flying with other drones at the same time, likely. And we also need to develop a method to autonomously complete the mission goals. So airdrop also for scanning and for waypoint pathing. So our hardware, we have the onboard computers, a Raspberry Pi. We're using the PixHawk as our flight controller, and we use for software-wise PX4, which is our flight control software. And ROS 2, which is going to handle our control messages, so messages between pieces of the hardware. Then, yeah, so basically this is our breakdown. We have everything in green is sort of one product. You can think of it as everything in yellow as well. Airdrop is slightly separate from everything because it may use implementation of sensors, but I can get into that later. So basically we have, path finding, a trajectory generator, and obstacle avoidance. And we also have a trajectory controller, which is going to be our method of controlling the motion of the plane. We need to integrate sensors to avoid hitting obstacles in the short term, as well as in the long term, which is sort of what our obstacle avoidance part is. For the sake of this and for explanation, we're keeping all of the different boxes separate for just to make it a little bit more convenient to understand. Also, scanning was initially considered as a separate function, but the competition layout this year and also the camera FOV means that we can do a scanning pass just a linear pass of one across the scanning area. Okay, so for pathfinding, we have implemented, or we're going to implement an RRT Dubin's pathfinding algorithm. So what is that? So basically it takes RRT, which is rapidly exploring random trees, and adds Dubin polynomials to the end of each segment of the path. And so that means that basically we have circular segments, or partially circular segments at each end of these straight line segments. And that's good because, well, first off, RRT is very fast, and it also takes turn radius into account. So because we're flying on a fixed wing aircraft, we can't turn on a single point, obviously. So we need to implement some way of taking into account the radius, the minimum turn radius that we can easily do. Also, it's we have an implementation of it in our previous code base, so it won't be that difficult to implement in this coming year. So then we have trajectory generators. So basically, we generate this path and it's close to being navigable, but it's kind of difficult for a controller to interpret a non-polynomial path. Also, we need to take into account the fact that our aircraft is flying in time, which is basically the difference between the trajectory and the path. So our trajectory generator is also going to check for collisions with dynamic obstacles. We're basing a lot of this on a paper from Adam Bree, the aggressive flight of fixed wing and quadrotor aircraft in dense indoor environments. It's a bit of a mouthful, but so basically it's one of the differences between what we're doing and what the paper does is that we are considering dynamic obstacles, meaning obstacles that are moving, right? So we're considering other aircraft, basically, and that's going to change basically the flow of how we're going to adjust for obstacles. So this is the obstacle avoidance, right? So there's two different types of obstacle avoidance that we're doing. We're doing dynamic obstacle avoidance, which can sort of be thought of as long-term obstacle avoidance. Basically, we're looking at other objects that are flying around us and trying to avoid pathing into where those objects are headed. So we're going to be using remote ID to obtain the obstacle location, speed, and altitude. And what remote ID is it's basically a way of determining, it sends back telemetry from drones. It's going to be mandated next year for use on drones. And the one consideration we had with that was that it's not going to be necessarily mandatory by the time that we're going to be at competition, but it's going to be soon after, and we expect many teams to have implemented it. It's also a lot easier than implementing some sort of visual system for tracking objects. Theoretically, if we couldn't do that, we would have some sort of either radar or some other sort of system on the ground that would be able to track obstacles in the air. We're going to be using Kalman filtering to predict the future state space of the obstacles, and then we're going to replan the path and the trajectory from that collision detection. And then we have short-term collision avoidance, which is basically you are right in front of another object and you do not want to destroy your plane. So basically, this is just sort of a last minute thing. It's a good safety feature to have, obviously, not just for our safety, but for the safety of other teams' aircraft. So we're planning on using LiDAR to map out a point cloud of objects that are directly ahead of us. We're trying to avoid immediate collisions, so sub 50 meters. And it's going to be an extreme high G evasive maneuver. So basically, some form of either pitching up or pitching down very quickly, gaining or losing a lot of altitude to try and avoid colliding with an object. And so, yeah, and you can sort of see the flow of our obstacle detection software. I need to move this out of the way so people can see. Oh, is there a question? Yeah, Charles.
Like, can you tell us what kind of LiDAR you're going to use?
Yeah, so there's a LiDAR module we're planning on using. I can't remember the name of it. What is it? Velovic? Yeah, Velovic LiDAR module. It doesn't release until next semester, unfortunately. So we can't actually implement it yet. But we're planning on, we trust the company that makes them. They make good products, generally speaking, and they're pretty reasonable for our implementation of it. We obviously this is a safety feature that we want to have on the plane. And we're likely going to implement it next semester. It's probably not going to be that difficult of an integration. We will likely have some sort of simulated way of determining like how well it would work.
So these days you need a permission from the Space Force to fly a LiDAR.
Oh, is that true?
Yeah.
Okay. All right. So we may have to reconsider. I don't know. Okay, we'll have to look into that. That's probably a good thing to consider. Yeah. Okay.
But you know, you're more likely to get a clearance from the Space Force than putting your hands on a velobike. That's my bet.
Okay. All right. That's reasonable. Yeah. All right. Yeah. We'll have to think about that later. Anyway, so basically, oh, another question? Yeah.
Yeah, this is James Coppert. On the common filtering, why aren't you just using the velocity and the position? Are you trying to do constant acceleration or constant velocity tracking, or what exactly?
So basically, the remote ID doesn't give us all the information that we want. Remote ID will give us the velocity and the position. It doesn't give us acceleration data or various other data that we might want for the obstacle avoidance.
I think the payoff there might be kind of minimal because you don't know if the pilot's going to keep holding a bank angle or if they're going to go straight again. So I don't know. I think that might be a marginal payoff.
Okay. Yeah, I think.
Yeah. If I may add, the Kalman filter is going to provide you some measure of uncertainty in the predicted aircraft position, which means that you can use it as a bound to do avoidance maneuvers.
Yeah, so basically our plan is basically to predict where now obviously it's not going to be perfect, but our trajectory will we're going to replan based on whether our trajectory will potentially collide with objects that are present in the with objects that may be in a certain position at a certain time. We don't I don't think that the uncertainty is going to be that big of a deal in that regard. Yeah, but no. Anyways. Okay, sorry. Okay, so this is sort of the flow of our trajectory, our obstacle avoidance function. So we have our path planner, which gives us a sort of global path of a path through our waypoints. And then we have our trajectory generator, which is going to generate a trajectory based on that path. And then we check if that trajectory is intersected by an obstacle, regenerate a path if it is, and if it's not, then we send the trajectory to our trajectory controller. And then one thing.
Yeah, so I was going to quickly say about that common filtering part. So Remote ID, they don't actually tell us, they give us velocity or speed, which is kind of interesting. They don't actually give us like a lot of like concrete details. So sorry, we're just using the common filtering to make sure, because I'm pretty sure they don't give us actual velocity. So just to get that information out. And also we did think about using the covariance matrices we get from the common filtering for doing stuff like obstacle avoidance, and that definitely might happen sort of like a V2 of this whole system. And then about the LiDAR, so LiDAR is currently our first sensor of choice because of that velocity bit coming out, but as you mentioned, I think Charles, that might be a bit difficult and maybe illegal for us to use right now. So do you have any other suggestions for sensors potentially that we could be using besides LiDAR sensors?
You know, typically people want to use cameras, for visual detect and avoid. It's a it's a whole can of worm that you have to deal with, because you have to have I think that you may be able to find training sets for detecting small objects over the horizon, but you have to have the right camera coverage and the processing on board. You can't process on the ground. So that's going to make things very complicated. As far as the LiDAR, I'm not even sure. I don't know if Velobit will have the right field of view. I mean, it's an interesting idea, but essentially that would be the most expensive thing you'd be putting on your airplane. You would have to do a ton of simulation to really validate that it's really worth it. I mean, it's avoiding something is worth it because you don't lose your airplane. But I don't know how well developed it will work, given the size of the targets you're looking at.
Another consideration we sort of had early on, whether we wanted to do some sort of stereo camera to figure out distance from that. I don't know.
Stereo, no, it's not going to help because okay, the widest baseline for stereo would be to put one camera at the end of each wingtip.
Right.
And you can easily compute the minimum depths that you can sense, or the further steps that you can sense based on your baseline and your field of view and your sensor resolution. And you would find out that it's not that great. So your depth sensing wouldn't be that great. And there is no way you would be able to keep those cameras in calibration because the wings would flex all the time. So it is a monocular vision problem.
Yeah. Okay. All right. Well, we're gonna probably have to reconsider that, but we don't have time, unfortunately. Okay, so we have our trajectory controller. Basically, phase one, we're going to be doing a basic positional controller. And yeah, so phase two is going to be an attitude rate controller. Sort of the first one's just simpler to implement. It's going to be the one that will serve as our base for later until we can get the attitude rate controller working. I'm going to have to go through these a bit quicker. So we have for airdrop, we're going to be path planning based on the wind. So as mentioned earlier, basically we're going to direct ourselves into the wind so that we don't have to worry about lateral motion. We're planning on using either AWAS or some sort of ground-based sensor. As we mentioned, we will have a weather station on the ground to detect wind, and we've basically just that would be our other option if AWAS is too hard to use. I guess it's a bit clunky. And then so we're going to have drop timing based on our parachute descent model. So for phase one, just a simple equation of motions. It's likely going to be just a very simple sort of projectile motion sort of thing, modified projectile motion model of some sort. And then for phase two, we might implement some sort of complex differential equation of motions. There's a picture on the right you can see. So that basically that would be an envelope in which dropping the payload would basically land it in our expected region. And then, yeah, so this is sort of our plan. We have, this didn't update. Okay, whatever. But basically we have by the end of the semester, we're planning on getting most of this stuff done. Pathfinding and airdrop are probably going to be done a little bit earlier just because we have a lot of that stuff already implemented from last year's code base. And then by next year, we're going to have a lot of bug fixing and working on our phase two implementations. Yeah. So are there any questions? Yes.
Are you even looking at collision avoidance? Is that one of your requirements for the competition?
Yeah.
It is?
I believe so, yes. We plus it's something that we sort of need to do. It's like it's a very good safety consideration to, you know, not fly directly into something.
Yeah, but I thought that the competition controlled the airspace.
I can add on to this.
Yeah.
Last year, for the first time, they flew 2 teams at the same time. So they said that that went really well. They're gonna fly 2 to 3 teams at the same time this year. And to make it fair, everybody has to be the same waypoints. Means if we're taking off, we're going at a different speed than another team. We'll be directly following them or them following us. We'll be pretty much putting ourselves on a collision course with other aircraft, with high likelihood. Especially in the airdrop area, where other teams are circling around at minimum altitude to get their airdrop, and we are also doing that same minimum altitude. So there's gonna be a high potential for it.
Is there any system that you can use on the ground to track where the other aircraft are? On board your aircraft?
Yeah, we were considering basically for the long-term collision avoidance. We were if remote ID weren't our choice, we would have gone with something like, you know, radar or some other sort of long distance tracking. You know, that may be helpful in the case of, you know, other you know, like short-term collision avoidance, but it may also be that, you know, we are far enough away and the other object is far enough away that we don't have enough resolution that we can determine for sure that we are in a collision path with another object. Also, it would just it would be a lot more difficult of a problem to solve in that regard, because, you know, we would have to not only get figure out whether we're in a collision path, but also, you know, send that information back and forth. And then, yeah.
Charles, do you have a question?
Yeah, if I understood right, you were saying your trajectory path projection was going to be based on minimum turn radius? Did I misunderstand that?
Yeah, so basically our when we generate our path, which is the RT Dubin's path, the circles at the end will have a radius that is equal to, you know, with a little bit of a buffer, the minimum turn radius of our aircraft, so that we can make as tight of turns as possible. It's likely going to be more smoothed out when we generate the trajectory, because the trajectory is sort of going to be padded out from the actual path. So it maybe we make more wide banking turns, but we want to minimize, because we don't have a lot of space in a lot of cases, we want to minimize the amount of area that we're using for turning.
Okay.
Are there any final questions? I'd like to open up the floor again, just to general questions, integration questions, any high-level concerns or feedback for the entire presentation. I know we went through a lot of information, but if there's something that's been in your head and you've been wanting to ask it, now's the time to do so.
So Matt, this is Rich.
Yep.
I don't know the past history of your air vehicle design and testing, but have you done any modeling, simulation, analysis, or testing of the control and aerodynamic characteristics of this aircraft with those bay doors open?
No, so that's something we have not done. We've talked in the past about you know, issues with vibration and whatnot, and you know, differences in pressure. That's not something we've done, and I know we've gotten feedback. We actually got feedback on that last year. Is that right, Eric?
Yeah, I can mention that one of the concerns that we got feedback on last year was the acoustics within the fuselage. We haven't done any modeling though, with the actual aerodynamic effects that it'll have on the vehicle as a whole when the bay doors are open.
Okay, so two things, you know, from a lot of directional point of view, you've just introduced 2 vertical control surfaces, roughly near the CG, so that doesn't hurt you too much, but you might get some vertical flow that impacts your vertical tail. That might, you know, if you get any crosswind at all. And then the air acoustics, you know, you imagine what happens when you open up your car door at 35 miles an hour. and or your car window and blah, 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 you get that vibrational effect. And the air acoustic shear layer, your magnetics that push that thing down, those bottles down, even though it's got weight, you got to make sure you got enough velocity to get through that shear layer. Otherwise it'll hang there, and you don't want that to happen.
Okay. That's good feedback. Thank you very much.
Matt, I can talk a little bit more about this tomorrow when we talk, if you want. I can give you some more background on that.
Do you have any recommendations for how to simulate that? Other than
So in my past experience, I did a lot of research back in a couple of projects ago, both low speed and higher speed. This is fairly low speed, but there's a lot of fundamental research that was done over many, many decades about weapons bays and shear layers and screw hole number modeling and flow modeling and what it takes to get through shear layers and things like that. It's pretty open literature. There's a lot of stuff out there about that might be helpful, at least understanding the phenomena. Not that you need to model it, but if you understand it, you can probably work your way through it pretty quickly.
Yeah, and I guess there's nothing against taking the entire fuselage and just throwing that into. We have a pretty big Boeing wind tunnel here. We could pop that in there.
I would just say if you're going to be in the wind tunnel with it, just slap on two reasonably sized pieces of metal or something, and just see what happens as you go up an angle of attack or maybe a modest side slip, and just see what happens.
Yeah. Cool.
Okay.
Any other general questions? From who? Charles, do you have a question?
Yeah, one thing that I was noticing was, you're using in your basic concept for the drop, you're using magnets and then overcoming them with an electromagnet in the middle.
Yes.
Seems like there's a potential for that to hang up on one of the magnets if they're not absolutely perfectly matched. I guess I was wondering if you'd be better off just having a system that had a single magnet and then a electromagnet that overcomes that in the same position. I'm just trying to keep it from hanging up in there.
That's a good point. I think we've also considered mechanical systems to overcome the magnetic force as well. That might be more consistent.
The main reason that we had the magnets separated so far was just to have 2 points of contact, and then it won't pivot around that one point. Because when the whole revolver is rotating around in the fuselage, if they're right next to each other on that one point, they can really pivot around that.
Yeah, I see what you're saying, but you could hold that mechanically, right?
Yeah.
I mean, just have pins.
Yeah.
Hold it. Anyway, just thought.
Yep.
That's good feedback. Anyone else want to generate some last minute thoughts before we close down for the night?
Matt, I just had one question. Somebody had brought up earlier just about the parachute, if anybody had any feedback between the two. Yeah. Is that just kind of being considered either of those concepts at the moment?
Go ahead. The feedback on the parachutes, both concepts.
Wait, which two concepts?
Sorry, in the presentation, I think there was 2 images, and I apologize. One of your teammates had said, if anybody had any suggestions between the two.
Yeah. So it was there's going to have to be a hole in the middle no matter what. But the one question that we were considering is whether we should attach strings to those holes in the middle. If we do that, it would look like the orange and black one. If we don't, it would look like the one to the left of it. That's something we have no experience with.
Yeah, I mean, if you do tie strings to the center, it will be a little bit more stable, but it's also just more strings that can get tangled. So I guess it just depends, what you're going to look at in terms of how that's going to get released. I mean, keeping it simple is always better.
Okay. Thank you. Question?
Sorry,
I have a question, but
parachutes. Can you ask about the hole size as well?
Yeah. So one of my team members was asking, do you guys know anything about how big that hole in the center should be? Is that something that we just trial and error or?
I don't know if you have any feedback on that, Elise, but Evan was asking about the effect of the hole size in the middle of the parachute on descent speed and drag.
Sure. So I don't have any, direct feedback other than, yeah, you're going to want to size that. So you can imagine you're going to basically hit a sweet spot at a certain point where once the hole gets too large, your actual surface area is significantly reducing. And then you would need at least strings in the center, but beyond that, you're also just going to need the surface area for drag.
Okay. Thanks.
Charlotte.
Sure.
What is the size of the bottle?
It's the standard water bottles, not like the half size, but the, I don't know, 16.9 ounces, I'm being told, 10 inches by 2-inch diameter or something.
8 inches tall, 2.5 wide.
Because you're spending so much energy on the packaging. I'm wondering if you actually need a parachute.
I think one of the main reasons that we do need a parachute is just because people are going to be standing like right in the drop zone, like judges will be standing there.
Okay.
Have to go retrieve the water bottle and check if the right water bottle is dropped to the right target. And it has to meet their standard of a safe landing. So we don't know exactly what that means, but we would, yeah.
That's a good point. Any final questions? In person? Final thoughts? All right, well, if there are no final questions, I'd like to thank everyone for attending our annual review. What I'll do after this meeting is go ahead and send out the presentation slides. If anybody has any lingering thoughts or wants to provide any additional feedback, they can do so by email. And then in the next couple of weeks here, we'll be taking in that feedback, reevaluating our designs, and then moving towards our critical design review, which is supposed to happen around the end of the semester. So once again, we'd like to thank all of you for the 2 hours of your time that you spent helping us review our project, and we'll make sure to keep all of you up to date with the competition and how testing goes throughout the year. So thank you to everyone online and in person. Hopefully you were able to learn about our project. And again, we appreciate all the feedback throughout the process.
Matt, when is the actual competition?
It's in June.
In June. Okay, thank you.
Yeah. All right, thank you.